Hello, everyone. Welcome to the 11th webinar in the joint Tran-SET webinar series, which will cover a variety of projects related to corrosion management system of transportation infrastructure for long-term durability, reinforced concrete structures from three quite different perspectives. So this webinar is organized by Tran-SET in collaboration with Dr. Homero in Texas A&M. So before starting this webinar, I would love that Dr. Homero provide a quick introduction about his lab and the main objectives and expectations of this webinar. Dr. Homero, I will turn it over to you now, please.
Okay, thank you very much, Moment, for the opportunity, and I hope that everybody can hear me. Welcome to this webinar, and starting, we are gonna talk about a little bit and briefly about the lab and the efforts that we do here at A&M in the National Corrosion and Materials Reliability Lab. So we have several clusters here. Of course, we named the National Corrosion Lab because the intention is to have all varieties and all kinds of topics here in the lab, from cluster in oil and gas, transportation, also infrastructure, architecture, and additive manufacturing, and automotive, all kinds of topics that we would like to pursue. Of course, that we are part of the Center of Infrastructure Renewal, which is part of the new campus at A&M. And basically, the intention of the webinar is to connect industry. And this is a very nice opportunity for us to do everything all the efforts that we've been doing with Tran-SET, which is a fantastic way to do research in combination for applications. So this webinar, the intention is to give a perspective of this topic that we have, of course, as main topic or critical topic for infrastructure, that is the durability in RC structures. So again, the intention is to link industry with academia. The academia side, we have Texas A&M, and we are participating in a project that we have from Tran-SET, and that project was co-funded by AZZ and also now co-sharing with CMC, which again is a project that we are targeting an application, and not only an application, but also an opportunity to do new technologies, new directions, and new ways of doing this collaboration between two important entities, which is academia and industry. So basically, that's the intention of the webinar. And again, thanks for your attendance. And I hope that this webinar help you to either start or answer some of the issues that we would like to do in these infrastructure issues or topics. So without any further, thank you, Moment. That's what I want to mention.
Okay, perfect. Thank you very much, Dr. Homero. That was very informative and interesting. So today we are having three experts presenting in this webinar. We will have three 15 to 20-minute presentations. So first, Dr. Homero will discuss the corrosion management system of transportation infrastructure. After that, Rob Kenschler will go over the regional steel rebar forecast and industry related statistics. And finally, Dr. Stephen Humans will provide a recorded presentation about galvanizing for corrosion protection of rebar in concrete. So again, the last presentation by Dr. Stephen will be recorded since he is unable to attend due to our time difference with Australia. However, please feel free to ask any questions in his presentation, and we will have this answered by the other presenters. And we will have the questions, and at the end of the three presentations, we will have a 15-minute group Q&A at the end of the three presentations. So please type your question anytime throughout the session. So without further ado, I will introduce our first speaker, Dr. Homero. Homero Castaneda is Associate Professor and Director at the National Corrosion and Materials Reliability Laboratory within Texas A&M University. He is also instructor for NACE certifications. He got his PhD in Materials Science and Engineering from Penn State University in 2001. Dr. Homero has 19 years of experience using electrochemical and non-destructive techniques to monitor interfacial phenomena in materials and theoretical modeling of corrosion, science and engineering, energy generation and storage electrochemical process for different industries. He has authored over 98 peer-reviewed papers in the area of corrosion, science and engineering, coatings degradation and reliability, materials characterization and electrochemical impedance spectroscopy. He holds 10 patents and copyrights. He is the editor of 3 journals related to electrochemistry, materials, corrosion, and pipelines. Dr. Homero, I will turn it over to you now.
Right. Thank you, Moment. I need to share my screen. I think you need to stop sharing, Moment.
Okay, yeah.
All right, then now I'm able to do it. All right. So I'm gonna do this presentation mode. Sorry, it's gonna take me like 20 seconds to.
No, that's fine, yeah, take your time.
All right, so I hope now everybody can see.
Yeah, we can see your presentation and we can hear you.
There you go, all right. So thanks, Moment, for a nice introduction. And thanks again for being here. And that's good that you show my picture while I was using Suit. I'm not using Suit anymore. I think that's the privilege of presenting by Zoom. But anyway, during the questions and answer, I will just put the video camera. This is a project that we did in this last year. And then we are wrapping this project with Tran-SET. And this, we call it corrosion management system for RC structures. And the PIs are myself and Dr. Ayman. I think he's listening also our talk. And without any further introduction in the title and things for this project. So the concept of this presentation and work was to present a framework for corrosion management. And of course that management you can define in any way that you think that is necessary for your system. In this case, corrosion, we are assuming that's the biggest threat for the RC system. So that's why we are putting the corrosion management. And part of that framework is the methods for corrosion evaluation. And I will point out some things that I believe that are a little bit different from the traditional, let's call it that way, for RC systems. And the way to characterize, how we characterize the corrosion process, also the techniques that we use and the methods that we use to follow corrosion. And finally, I'm gonna just talk about the modeling. We call it deterministic, and nowadays we are more probabilistic. So that's how we are doing this framework to just create a management system. And the objectives for this work are, of course, based on the summary, is the characterization. I'm gonna start with the characterization of one element of the RC system. The RC system is an electrochemical system. That's the corrosion perspective, which the rebar is the anode and cathode, and the concrete is gonna be the electrolyte. So we are gonna start to mention this characterization, the methodologies that we use to characterize these elements. And again, we are gonna characterize one of the elements that we believe that is a little bit of missing in terms of all the traditional work that is being done in this area. And the methodologies will overcome, we are gonna have the results, and then we're gonna postulate some models that give us answers. And of course, that based on that answers and that models, we will start to give some reliability approach. And therefore, we encompass everything in a framework for corrosion management. This is the perspective that I'm mentioning. You see on the left drawing or schematic. I hope that you can see my, my pointer. So on the left, you see the schematic, the typical. I will go very fast because I think that most of you knows this, the rebar, the concrete that needs to expose to the environment. On the y-axis is time, on the, x-axis is time, y-axis is cumulative damage. So with time, you see that the precursors of corrosion penetrate, migrate, diffuse, and touch the rebar. The rebar has a thermodynamic passive layer. Once it touches, and there is an accumulation, we call it threshold. And then when that threshold is met, of course, it depends on the system. Then from the initiation part, it will go the transition or propagation, which we call it active state. And that active state will also form corrosion products. That propagation state, you see the accumulation damage can go in this direction, can go even with a higher slope, but that's the schematic. So what we are doing in this project or in this approach is that we are putting an additional, let's say, protective layer, not only the passive layer that you have originally in the steel, but we are putting a galvanized. And we know that this is not a new technology, but it's a technology that we think that is worth to explore in detail. Why? Because we have this same diagram that we are saying that we have the initiation. As you see, we are assuming that the initiation of the same process as on the left is gonna last more time. Why? Because once the precursors of corrosion touches and migrate into the concrete and touch the zinc layer, what is gonna happen is we're gonna sacrifice, it's gonna react, the zinc is gonna react and it's gonna start to dissolve, and also it's gonna form corrosion products. And we are doing this characterization that the corrosion products are more uniform than this. And you see the schematic, these are very heterogeneous, very thick. In here is more homogeneous. That's why we are saying that the cumulative damage still is on stable state. And after we have a certain point, let's say now this will be the activation time for this schematic. The activation will be once the precursors of corrosion, in the common language is chloride, but it's also oxygen, will go and penetrate and dissolve the sacrificial layer. And then we're gonna start to have the propagation. Of course that we explore different also systems. The other system that we explore is that the passive layer will be different, which means that the rebar has a certain components, and we name Chromex, for example, the Chromex steel, that we have components. And the theoretical aspect is that this layer will have an impact in the properties, but also we add the galvanized layer and see that the hypothesis is that we have a cumulative damage constant with time until we reach the metal. But also when we reach the metal, we will have maybe a longer protection. Why? Because we have this passive layer, which we need to explore what is gonna happen if the chloride will go and touch that layer. All right, and the last system that we are gonna cover is when we add the epoxy. The epoxy is another layer that we are adding, and you see there are different stages before the epoxy or the layering the epoxy, and also the galvanized layer will last until we reach the metal. Of course, the normal say is that the more layers, the better. Well, sometimes no. In terms of corrosion, that's why we are putting the stages, that the accumulative damage is gonna be very, it will take time for the epoxy, but I think there are studies that says that, or that shows and demonstrate that when the epoxy is no longer there, we will have a local condition, and the epoxy is a very nice cathodic side, and this is a very nice anodic side. So maybe the accumulative damage will be higher, all right? So therefore, what we did in this project was to do the characterization, and I will go very fast. We use electrochemical methods. Why? Because electrochemical methods that we use in the lab, we can extrapolate in the field. We know, and we did some search, And we know now how the field, the programs that they have in the field for inspection of the bridges. So I think that there is a lot of variety of techniques that they are using, but we believe that the electrochemical techniques gives information for the rebar, which is the one that gives the capacity to the RC elements or the RC structures or the RC systems. So what we did is that then to put different rebars in a simulation of the concrete structure. And we have, we did the experiments with time. And this is important to mention that this experiment illustrates the activation state. The activation state means that we suppress the time of the diffusion of the precursors of corrosion within the concrete. So we have these results going with time. And you see that, for example, 615 grade is going to be the ASTM pure rebar without any layer. And the conclusion here in these plots, just by reading, is that, of course, from day 1 to day 30, the rebar is active. Of course, we used a threshold that overpassed that threshold to activate the system. And with time, we are going to dissolve continuously this rebar. In the case of 767, which is a galvanized layer, we have this behavior. You see even in the activation state, which again, we just are neglecting for now for this set of experiments, the initiation stage. Then we have this behavior. And in impedance, the important part of electrochemistry is not only that gives let's say, the equivalent of the corrosion rate, but also the corrosion products, how they are forming, how they are evolving with time, which is important for the durability and also important for reliability of the RC system. So in the 767, we have a response of dissolving. So we have a very good sacrificial effect. Therefore, the galvanized layer is dissolvent with time. Also the 1094, which is another process, let's call it that way, another rebar system. So we have a galvanized, and there are differences. It's not only the difference between a steel and the galvanized, but also between galvanized systems. We also saw differences, which we're gonna talk very general here in this set of results. So, and the next one is gonna be the 1035 grade, which is the one that we mentioned, is the Chromex, which is a rebar with different composition, and also the galvanized layer. And we see that the response is different from the pure galvanized 767. So, and I will show you what it means, these results, all right? Because you see different, and I can elaborate more at the end, how this Nyquist on the left and the body on the right and the face angle will give you information of the degradation process. That's what we care in terms of these results, the degradation and the information that we can extract, which I'm gonna elaborate a little bit later. So 1055 is a system that contains the rebar, the plain, the flat steel, I call flat steel, and the black steel. I think that's the jargon for civil engineering, and the black steel with the galvanized and also epoxy. And the only thing that I want to highlight, of course, in this representation is that the impedance you see is 10 to the 11, previously is 10 to the 5. And what it means that I'm going to explain later. But the thing is that we did this characterization and we give a first approach for different rebar systems, all right? Based on these techniques, what we could do is the elaboration of modeling. This is the deterministic part that I mentioned at the beginning. Deterministic is with constitutive equations, which gave us the opportunity to elaborate and to characterize and quantify what is happening with the corrosion rate, with each one of the corrosion products that we have with different rebar systems, and also what happens in the solution, everything at the same time with this technique. So we could use very simple way to explain what is happening, and with numbers and with, we call it equivalent circuits, which I think is a better and easier way to explain rather than chemical equations or transport phenomena. So this is the other equivalent circuit that we use for these systems that are systems that, what they have in common is the galvanized layer, but nevertheless, they are different substrates and different processes. But this is the model that we use deterministically. Now, the other model that we built was with the epoxy. That's the model that we create and we have with this epoxy system. Now, what it means to have the model. What it means to have the model that we can explain quantitatively what is happening. Now I can tell you in these two diagrams. I'm going to explain only the steel, bare steel, only once, and the rest I'm going to go and focus on the other systems. So you see on the bottom part the rebar that is that has the typical initiation and propagation. And remember that we mentioned that the first set of experiments were simulating the activation, which is the propagation. We started from this point, which means that we skip the process of diffusing. All the components that goes to the concrete, penetrates in the concrete, diffusing the concrete, we skip that process, and we are in this stage in the steel, all right, which is the initiation. Now you see the response that the impedance or the corrosion resistance in this case, and this based on the model that we built, the corrosion resistance goes down with time, you see, and goes down and it reach a plateau. That means that the corrosion products are already formed. However, the resistance is very low. Now what happened with this system, the 1094, which is a galvanized system. Remember, that's the layer, and we start at this point, the activation point, because we avoid this diffusion. What happens with this layering, the zinc layer? Well, what happens is that you see the resistance of corrosion goes up but goes down. Why? Because the zinc is sacrificing, is dissolving at a higher rate than the steel. That is good because it's protecting, all right? But it's dissolving with time. And you see that there is a plateau, and there is a point that is gonna increase now the resistance of corrosion. Why? Because we are forming a very nice uniform, and this is the hypothesis, and we need to elaborate more in this hypothesis later. We are building a very nice corrosion products layer, all right, with time. That's why we have corrosion resistance for the zinc layer higher than the corrosion products from the steel. This is what it means, and that's how we build the model to explain in detail what happens with 1035, which is the other system. The steel is pretty much the same. I'm not gonna elaborate in this, but you see 1035, which is another galvanized system, and we start from activation point. You see that the resistance of corrosion is activated at the beginning. Of course, the zinc activates and starts to dissolve very fast. That's why the corrosion rate is low. Then start to be, we call it Tran-SET state, and then reach a plateau. And then the uniform corrosion products also increase the corrosion rate, corrosion resistance. So that's what happens. And still after, I can tell you this is a scale of logarithmic scale. So this is after 360 days of activation, we haven't reached the steel yet. As of today, we have 200 days, 420 days, and we haven't reached the steel yet under steady state condition, which means that even in the activation, if we compare steel with galvanized layer, we haven't even reached the state of real activation of the rebar, which will give another mechanistic process. Now, of course, with epoxy, this is an epoxy layer. And you see that the corrosion resistance is very high because why? Even though we don't have any concrete, we already reached the epoxy, the activation stage. and then we have very high resistance. However, it's worth to wait to say what is happening when the epoxy and the zinc layer doesn't appear anymore. Maybe this is just a trend. This is a trend. This is not for sure what happens, but this is a trend theoretically what could happen if we have a local condition in the epoxy. What we did also is to characterize the corrosion products to be sure that we are have a uniform system. We did this with the fog chamber. I know some of you don't like fog chamber because accelerate doesn't represent anything. I think I agree, doesn't represent performance, but we use it to see and to accelerate the process. And you see here, to accelerate the process and see how the distribution of corrosion products are. You see on the top, you see our corrosion products based on the iron and steel, pure steel. So you see how not only you see the thick yellow and different colors, these are thick, so which means that you have not only more dense, but heterogeneous distribution. And you see that on the galvanized layer, you see that is not high volume, and also the distribution looks more homogeneous than the steel. It's just, again, it's just to see the distribution. We are not saying about performance, all right? We are just seeing the distribution of the corrosion products. We also did, of course, without doing the RC systems, I think that we are missing a very important part. So that's why we set up the system, but with systems that we start to do the whole RC system, which is the concrete part. And we did electrochemical testing. And these are the characteristics that we have. We did one water cement system. Why 0.53? Why? Because we want corrode it faster, or we want to uptake the water faster. And we know that this is the water cement ratio that we can use it for sure that we're gonna reach that stage faster than the others. And these are the characteristics of the system. And the rebars that we have, of course, are the same one. And I just want to illustrate the results. Now, based on the modeling, based on the schematic, you see that, for example, if we have the RC system, you see that this is the uptake of the water, all right, of the electrolyte. We use 3.5%, which is way more than the threshold. So the water penetration, you see that's why the corrosion resistance in terms of the impedance is not very different from steel that galvanized. Why? Because it hasn't reached yet the rebar, all right? That's why you see a similar behavior after 100 days, which means that we are at this stage, all right? At the initiation stage, everything is equal. Why? Because we have similar, not equal, sorry. Similar because we have the concrete that is the one that is putting the barrier. Once we pass the concrete, everything is different, all right? So that's why, even though we compare to a galvanized system, is pretty comparable. So the first stage, which is the initiation stage, it has to be overpassed. I think we have now 250 days. We're gonna cut another sample to see if we reach the stage, but we're sure that the electrochemistry will give us the answer. And also we have the model to do some extrapolation. We can do extrapolation theoretically, but I believe that the model is not valid until you do it experimentally. So I'm gonna touch base in terms of modeling very fast because I don't have too much time. The model is the typical model. Everybody knows this model that is based on diffusion-based model. That is the typical Fick's law. And you see the concentration based on the concentration of chlorides. You have a certain corrosion rate, and then you can do your assumptions that if the model is based on the diffusion coefficient or is this based on different parameters, and we set the parameters, model A, B, C is based on different components of the concrete, either the water cement, current days, distance of a source of chlorides. So we did that, and then is also, we have this reference, we report this. And this is the probability of the initiation time, the initiation based on the characteristics of the concrete. But we are building the model, the same model, because now we have the deterministic part, and you see That's the classical on the top. In the bottom, now we can see in terms of probability, and based on what we did, and this is what we did, the modeling for each one of the rebars. This is our model. Now we can set the corrosion rate based on the characteristics of the rebar and the characteristics of the signal that we got in the lab. And we can extrapolate this setup and not setup, sorry, this equipment and this methodology into the field, all right? So, and that's at the end of the presentation, I'm gonna mention this, but that's the classical reliability model you see on the left. This is pretty much what we built with the corrosion rate based on the characteristics of the concrete. On the right, you can see the characteristics not only of the concrete, but also the rebar. And at the end, both components, both corrosion rates can be now following the classical reliability model that is based on the area, the change of the area of the rebar, and that puts a capacity, and that puts a reliability in terms of a function state which is defined here in G, and is based on the area that is decreasing. This is based on corrosion rate, general corrosion rate, and the capacity based on the loading. And we have this behavior or this outcome or output based on the classical reliability modeling. And you see that this can be repair based on the concrete, or repair or an action based on the rebar. This is one of the things that I want to point out, and this I'm going to do it fast, but nevertheless it's very important that the model that we are also doing in this project is localized model. It's not only the general approach that I've seen that most of the literature use. It's the general model is corrosion rate, but we now can prove that the localized attack is more threatful, which means that you have, let's say, 20 MPYs in general, but there are points that you have 30 MPYs. So that's why we built this model, and we are validating this model as we speak, all right? It's based on the rebar. It's not only our general corrosion, but this is the shape of the pit. Of course, it's an ideal geometry shape. We are doing this experimental study. We built the model, and this was a work from LSU that they built the model based on the literature, but now we are putting the model in terms of validation of the experimental results based on the localized. This is the reliability approach that was performed, and these are some results based on the literature. We now will get results based on our results, based on the rebar and how the pits will change the reliability approach, or sorry, the probability of failure, and also the reliability. So this is very important to mention. And this is the last stage of the presentation, which we're gonna build the corrosion management based on what you hear. Based on what you hear, of course, this is corrosion based. So again, we are missing a lot of components, we know, but we are assuming that corrosion is the main threat. So that's why we see these diagrams. And the last stage, which I hope we can do it this year, we already have identified the bridge, but it's very far from Texas. And we know that the current situation, because of COVID, we cannot go that far in terms of permission, all right? But we are working in terms of either Arkansas or Oklahoma. And I hope that Texas gave us the opportunity to do this monitoring, which we are ready to monitor with the techniques that we have, all right? And with this is the parameters that we are gonna get without destroying non-destructive evaluation, all right? Non-invasive, non-destructive evaluation. And that's pretty much it. Of course, acknowledgement, thanks to Tran-SET project, the number is there. And of course, the funding, cost-sharing funding from ACC and ZMC. Thank you very much for your time. I think that's pretty much it. Sorry, I think I passed the limit.
That's fine, Homero. Thank you very much. That was excellent. We really appreciate it. So now I will introduce our second speaker, Rob Kenschler. Rob is the Greater Southwestern Regional Manager at the Concrete Reinforcing Steel Institute. He worked for 15 years as a design engineer, designing power plants, paper mills, and other industrial facilities. Over the past 16 years, he has been promoting either structural steel with AISC or reinforced concrete with CRSI. Rob, I will turn it over to you now.
Okay, great. Thank you.
Let me stop sharing my screen first. Okay, you can share your screen now.
Let's see here. Okay. Oops. Great. Does that look good to you, woman?
Yeah, I can see it.
Oh, okay.
Yeah, and we can hear you too.
Okay. Well, Momin, thank you for having me here, and I appreciate the time that you've given me to speak. My name is, again, Rob Kinchler. I'm a structural engineer and regional manager for CRSI. We're the Concrete Reinforcing Steel Institute, and we have been invited to this through CMC and AZZ to help speak here, and we're glad to do that. CRSI is the trade association for rebar. We were founded in 1924 to represent our industry members, and we do maintain industry standards and specifications. We also do a lot of development of technical fabrication help. We provide design assistance where we can, do a lot of research. We usually combine that research with other organizations to help leverage the amount of research we can do. And then we also promote the use of reinforced concrete in the construction market. Today's presentation is going to be a little bit about that market. And our members consist of the producers, which would be your steel mills, CMC, Gerdau, Nucor, Structural Dynamics, Evraz, Benton Steel. And then we have many fabricators that exist throughout the United States. There's probably close to 250 members, but there's probably another 150 fabricators that are out there that are non-members. We also represent placers, which is the equivalent of a steel erector, that take the rebar that's been fabricated in the shop and put it in place in the field. And the other members that we represent are the suppliers of related products like tie wire, bar supports, couplers, headed anchors, that kind of thing. If you guys are interested in becoming members of our association or institute, on our website, crsi.org, it's easy to join with the clicking on the CRSI membership. I am offering right now, anyone that would like to join, a free design guide that we promote, or we publish. There's several to choose from. So if you guys are interested in that, let me know. Our publications include these design guides, which you see here on the left. They cover a variety of topics from the design of columns, beams, diaphragms, pile caps, handling vibrations of floors, and even exploring some new forming systems that have come over from Europe recently called voided slab. We also produce tech notes on many topics, including those related to corrosion, epoxy, coated rebar, galvanized rebar, stainless steel, MMFX, which is the chromium you just talked about. So we do that as well. We have manuals on field inspection and placing rebar. Of course, our main publication is our manual standard practice, which covers all the requirements for detailing, fabrication, placing, estimating, those kind of things. Our newest publication is the design guide on ACI 318. This is a approximately 1,000 page publication that goes over example problems for every code requirement in the newest ACI 318 building code. So the 2019 version of the ACI 318 was published this year. And this actually has design examples all brought together in a convenient manner so that if you design a column or a beam or slab or what have you, all the appropriate code requirements are there, and it makes it easier to go ahead and do your design. So this would be a great free book if you were to join today. Our tech notes, like I said, include topics of multiple varieties, many of them on corrosion and durability of rebar. So I always recommend those are free. You can access those through our website. We answer a lot of frequently asked questions with these tech notes. We also have a design center that is available if you do a project, you're looking for a conceptual design to start your project with, or to compare to, say, another building material like structural steel or wood. This design center can give you a quick and output that you can then take to general contractors to look at pricing. A program that we provide for free on our website is called CRSI Concept. It lets you analyze different floor systems for gravity loads to determine what might be the most economical systems. They cover everything from wide pan joists, drop panels, voided slabs, flat plate, and one-way beam and slabs. It's a very quick program you can use. If you have the majority of your information ready, you can get a design done in about 5 minutes. We promote concrete also by handing out awards for projects that are designed in concrete that have some sort of economic, aesthetic, or innovative technique to them. This was the Austin Central Library, not too far from Texas A&M, and it was a winner back in 2018. We just handed out our 2020 awards about a month or two ago, and don't have those ready for a slide yet, but did have one that was submitted by our mill in Texas, CMC. Rebar fabrication begins in a shop. Here you see a typical shop layout. If I get the pointer here, let's see if I can find that. Oh. I have don't know what I just did, Mona. Let me see here.
So what's the problem again?
There we go. Okay, I'm trying to get back to full screen. That's the problem with using. I did it again. Let's see. Oh, here's the pointer. Okay, there we go.
Okay.
So I don't know if we're on full screen here. Can you still see full screen, or do you see closed captioning? I'm seeing closed captioning.
I see we can see the captions. So we can see the full screen with the captions.
Oh, there we go. I'm back to full screen.
Yeah, now it's a full screen.
So apologize for that. So this is a rebar, typical rebar shop layout. Back here, you can see the inventory of the rebar. It's come into the shop. This is called your shear line right here. In the middle, this red element is your blade, your cutting blade that takes the rebar from inventory. They run it through to the appropriate lengths. And then down here, you have hoppers that can sort the cut rebar into appropriate lengths. This is a close-up view of the inventory. They'll stack the rebar by grade, by size, and by length. So that way you can easily, by crane, select what you need for your particular job. This is a close-up shot of the shear line, and I'm probably going to take you back to the other shot here in just a second. But if you see that shear line right here, as they bundle these, or as they cut these bars to length and put them in these hoppers, the crane will then pick them and place them on the truck for delivery. Some of the cut bars will actually be taken over to another station where they will actually bend the bar. Also, pay attention right here. You'll notice these coils or spools of rebar. This type of rebar is produced in a mill and is set up for an automatic bender. I'll show you that picture here shortly. This is the bending table that you'll typically see in a fabrication shop. The rebar is placed around a bending pin. These are all pins set to make sure that you do not initiate any undue deformations. You are getting obviously an elastic deformation here, but this is not a problem for rebar at this diameter of bend. But the large pin creates the diameter of bend. The small pin right here in front is what grabs the bars and bends them into a hook formation, either 90, 135, or 180 degrees for developing anchorage in concrete so that you can resist the pull-out loads. This is an automatic bender, and you'll notice back here those coils I just showed you. Here's a couple sets of coils. The coils are grabbed and brought through a straightening machine, which take out, twist, and straighten the rebar. They're fed in here through this cover plate. And as you come out here, there's another rotating table like the manual bender we just saw. And this can do multiple shapes very quickly at a time. where the operator can then take the bars and place them, the finished bars, and place them on a deck ready for shipping. So these are typically going to be your ties, your stirrups, that kind of thing. CRSI has been working with the PanCal Foundation for the last 5-6 years plus. Did a lot of research over at UTSA, the University of Texas San Antonio, on high strength rebar. So there's a movement now that we're going to be trying to push grade 80 to replace grade 60 as the go-to rebar for the majority of projects. That will probably take, 4 to 5 years for that to occur, maybe a little longer. But you can see right here the difference between the amount of rebar required for the same type of load. This is grade 60 rebar right here, grade 80 rebar right here. Your openings and the amount of rebar are quite, well, the openings are quite big. The amount of rebar is quite less. And even though it costs you about $60 a ton more, it's much easier to place this rebar and then to consolidate the concrete around the rebar. This leads to great job savings, better constructability, better productivity. There are some differences with the higher grade rebars you all are probably very aware of, and that is your development lengths are going to increase. And you have to be careful about brittleness. The research showed us what our tensile to yield ratios had to be and ductile elongation requirements had to be so that the energy absorption would not be destroyed by going to a higher strength rebar. We also talk a lot about coated rebar at CRSI. As Armando just mentioned, we do promote a lot with the galvanized rebar that he talked about, the dual systems, the 1055 he just mentioned, and the 1035 low carbon chromium. It's interesting, I think it was mentioned that I used to work for AISC, the structural steel group. Their galvanized structural steel is very common in the concrete rebar world. You do not see that as much. Epoxy tends to be the kind of the overall choice, I would say, but I am seeing galvanized now taking a greater impact in the market, and I think that is a wise choice to look at both these systems and see what best fits your needs. CRSI is a big proponent of reinforced concrete pavement. There's a website that's available for that, and since you guys are part of the Transportation Consortium, we work with a lot of DOTs and trying to promote the use of CRCP, which is continuously reinforced concrete pavement. State of Texas, the DOT there, are big proponents of CRCP. They're slightly different than jointed pavements, so they obviously have no joints and the reinforcement is continuous, but they allow for long-term low-cost maintenance. There's a little bit of a higher initial cost, and but the success with which Texas has been able to utilize CRCP in their highway design tends to give me pause when I look at the problems other DOTs have with either asphalt pavements or jointed concrete pavement. I was asked today to talk a little bit about our reinforcing steel market, the economy, and some of the things going on in the government, the federal government, with regards to infrastructure development. So that's where I'm going to kind of turn my attention to now. CRSI twice a year puts out reinforcing bar forecasts and consumption reports. This year, the first report was put out in June. We'll put out another one here in about a month. We get data from the Portland Cement Association, PCA, as well as Dodge Analytics. They're a well-known forecaster of data and the amount of jobs that are being built right now in the United States. We also get from SMA, Steel Manufacturers Association, the amount of rebar that is sold in the United States. And we combine all this information to come up with the amount of rebar that's consumed. And we can kind of help reconcile that with our mills and fabricators. The basis of using PCA, which are the Cement Producer Association, is that cement usage and rebar usage track very well together. This is a chart going back to 1945 showing the consumption of rebar with the consumption of Portland cement. So what we've noticed is if we can use Portland cement as our statistic, as our go-to, we can correlate rebar usage with it in order to help forecast future consumptions. This is a chart here showing from 2007 till 2019 consumption data in the United States. Currently, there's about 8.7 million tons of rebar consumed a year. Of that, a little over 1.5 million tons of rebar is imported. The remainder is domestic for a total of about 8.7 million tons. You can see that prior to the Great Recession back in 07, 08, rebar usage was over 10 million tons. We have not come back from the Great Recession drop-off of 12, 13 years ago. When you break down consumption into the different markets, and here we break it down regionally as well as via market, you can see how we consume the rebar in the different marketplaces. Of importance to you guys would be highways and streets right here. The total market consumption of rebar that's used of that 8.7 million tons, 30% of it is in highways and streets. So it's quite a large market for us. Interestingly, though, that market has stayed pretty much consistent throughout the last 12 years. It's been about 30%. And if you go back to this chart here, you know, we've in the last 10 years have varied between 6 million to 8 million tons. But the 30% number has been about the same. What that tells us is that the amount of concrete pavement with reinforcing has not drastically changed much in the overall market. CRSI is trying to work to help change that. But when we look at our forecasts, turning from consumption to forecast, there's several triggers that you can use to give you an idea of where things may or may not be headed. One of the best ways from the construction industry is the AIA Billing Index. Now, the AIA stands for the American Institute of Architects. Architects tend to be a good leading indicator of future work since they will get the jobs that come from the owners, and that will happen before an engineer will design it, or a contractor will build it, or a fabricator will fabricate it. In this index, they use a normalization procedure where 50 is considered neutral. Anything below 50 on their surveys from their architects is a declining construction environment. Anything above 50 is a improving construction environment. Here you can see that over the last year, we were doing very good until coronavirus. And here's the coronavirus fall. And now we've seen quite a drop off with architecture firms, and they're starting to see things pick back up. Now, the difference here is that there's also a contract line. How are they doing actually signing contracts? And how are they doing on actual inquiries? So this is an owner going into the office to, ask about a possible job. This, in other words, indicates owners are showing more interest with architects, and it's a positive sign right now. It's above 50, which is a good sign for leading work. If you look at it regionally in the architectural billing index, the South, which is our region, including Texas and Louisiana, we're on the lower end right now. We're not as bad as the Northeast, but we're not as good as the West or Midwest in terms of the outlook. It's still a slightly contracting environment, but as I noted before, there's been a trend towards improvement. So that's a good thing. Also, the Dodge people who we get data from on forecasting have their own momentum index. Now, this is based on construction starts. So these are jobs that have been signed. The momentum index actually increased about 4% the last month from August to September. And that's the third straight month of increase. So this would be work that's being signed, not work that's being inquired about. That's a big difference. So those are two good signs for future forecasting. Now, PCA, who we get some of our forecast data from, and they're one of the top forecasters in the United States. Interestingly enough, the cement guys. I typically get forecast data from them twice a year, sometimes 3 times a year. The report that we put out back in June had a 2020 forecast. This was revised for COVID, of a negative 3.8% contraction this year, and then a 1.5% improvement next year. The fall forecast came out to me just last week, so I actually stuck these numbers in here. You'll notice that the 2020 number went from negative 3.8% to negative 1.2%. So there's an improvement there, not as bad a contraction as first thought. The 2021, though, that change is a decrease from what was previously thought, a 1.5% improvement to a negative 0.5% contraction. And the reason that is because there was quite a bit of drop off from when the COVID outbreak first broke till about the end of July. A lot of owners weren't doing anything, and that's where it actually, we shifted our delay of new construction out 4 or 5 months. And that's why you're seeing that movement into 2021 on a contracting environment. Excuse me. On this new forecast here, I pulled off some of the numbers. They actually predict that the GDP, a good leading indicator, they predict a contraction of negative 4.4%. I have seen not too long ago, about a month ago, estimates of about a negative 2.6%. So this is not as bad as originally feared back in March and April. They were talking about much larger contractions. That's a good sign. And you also see that Portland Cement Association predicts an increase in GDP for 2021. Now, like I said, because the construction industry is a lagging industry, we're seeing some negative trends for next year. But overall, this is a good sign for the construction industry coming back. That has to do with the fact that once a developer, owner, or even municipality like the US government decides to pull the trigger, there's a lag between pulling the trigger and getting the design done, ready to be built. If you go to highways and streets, I have 3 lines here. Line 1 represents the billions of dollars spent on highways and streets at a inflation-adjusted $2009 range. So that way you take inflation out of the picture. That's this line right here. You'll see that for 2020, the market improves just slightly, or actually stays even for the most part, between 2019 and 2020. That's due to the fact that work that was already designed is being built. But then you will see a slight reduction for 2021, which correlates to the negative 1.5, or I'm sorry, negative 0.5% reduction we saw on the previous slide. You also see down here that line 3 represents the change of concrete pavement production. So like I told you, we've had about a constant 30% consumption rate of rebar for the highway market. That's using continuously reinforced concrete pavement. And you can see down here that we go from a negative, we're going to lose a little bit of share here in 2020 and even quite a bit more in 2021. So for us, that's not a good sign for the concrete industry. For Portland Cement, it's about what we'd expect. We're actually doing a little bit better in terms of contraction compared to the GDP. And we do have a contraction here. That's the leftover I told you about due to the lag compared to the increase in GDP for 2021. But to again summarize, the AIA Billing Index, the Dodge Momentum Index indicate that things are looking better if we can continue on that path. So, excuse me, if we take that out now to the forecast, we will combine our Dodge data and our PCA data, and this is based on the June report. It is not the latest numbers. You can see here that our overall forecast for rebar consumption drop off quite a bit for 2020. Now, when I say quite a bit, we were at 8.7 million tons right here for 2019. We're going to drop down to about anywhere between 8.3 and 8.25 tons. These are from 2 different forecasting groups, Dodge, PCA. And I usually don't put too much stock in the numbers more than 3 years out. So I kind of neglect these over here. It's a lot of magic that goes on, but usually the first 2 years in the forecast are pretty reasonable. So you can see that one PCA, I told you a minute ago, had a 1.5% increase for the June forecast. They revised it down to a negative 0.5% decrease in this forecast here. So it kind of comes back more to what Dodge was saying with a negative 5.3%. We break up our economic forecast into regions because each person that does what I do as a regional manager covers a certain territory. My territory actually includes the South Central and New Mexico and Colorado from the west. It's not exactly our territories, but it's close enough with what Dodge data gives us. So we break down our forecasts into regions so our members know what they're getting. But this is applicable to you as well, since we're part of the South Central. Texas is in there, Louisiana's in there. You can see that we weren't looking as good in the June forecast. We had about a 5% average decrease for the next 2 years, this year and next year. That's something that, you know, our manufacturers, fabricators, contractors will want to take note of. We also forecast in different target markets. I think the one that's pertinent to you guys is highways and streets, but we also track office market, healthcare, multifamily. The COVID situation has really changed the paradigm for the office market. There's a big move to stay-at-home work, and it looks like the office market may not be in high demand as it used to be, with people now getting used to working from home. Healthcare, is still in need. Multifamily, the market there has been strong, and then highways and streets, like I said, we'll look at. But the forecast for office, again, this was from the June forecast, is actually pretty good when you look at 2020 and on for Dodge, and then a reduction in 29 and for PCA in 2020, and then a slight improvement after that. But this was done before people noticed that there was a paradigm shift possibly in the need for office space in the future. So that will probably be revised in these fall forecasts. When it comes to healthcare, they show a drop this year just because of new work, but then an increase going on out, which is what you would expect, and that's actually borne out with what we're seeing in the AIA and Dodge Momentum numbers. Multifamily, these numbers here I think will actually be revised up in the fall forecast. This was the original, but the multifamily market has been very strong, even though of the COVID situation. There's still been quite a demand for multi-story residential as well as single-family residential housing. And then highways and streets. Right now, I said there's actually a slight forecast of increase for this year. Or basically stay the same, which is what's been bearing out in the numbers. And then a decrease next year, which is what PCA was saying. Dodge forecast a slight, basically the same increase. 0.8% increase is staying the same. And then there'll be a gradual uptick. In terms of the actual United States government and what the Congress is doing with regards to funding for highways and streets, right now the problem is that for us especially, the highway bridge work represents a significant percentage of all the reinforcing steel consumed. And if there's not continued funding, that's going to hurt our members and also hurt the state DOTs and people in general in terms of keeping the infrastructure of our nation, at an average level. ASCE, which is the American Society of Civil Engineers, continually rates our infrastructure at a grade C or grade D in the poor category compared to other competing nations. Right now, the highways and streets are funded pretty much with an instrument called the Highway Trust Fund. That money that comes into the trust fund is generated primarily by fuel tax. That fuel tax has not changed since 1992 with regards to inflation. So the purchasing power the fuel tax provides is less and less, but it generates about $40 billion a year in revenue for highways and streets. But the trust fund spends about $60 billion a year. So they're running a deficit. Back in 2015, they passed what they call the FAST Act, which was a legislation that was meant to fill the gap here, the extra money they needed to keep the Highway Trust Fund from going bankrupt. That expires it actually expired in the end of September. So the Highway Trust Fund also provides over half of what the state DOTs use in their budgets every year. So this is a huge problem right now in the United States about what are we going to do if the money runs out on highways and streets. So as far as CRSI is concerned, we are supporting Congress through lobbying efforts and partnering with other organizations like CRSI to find a answer to raise revenue for the Highway Trust Fund. As I mentioned, the gas tax has been stagnant and not changed and does not get adjusted for inflation, and therefore is not the permanent solution. And so we're doing a lot of lobbying with regards to that. But this year, about a week ago or 2 weeks ago, maybe, the FAST Act was extended, even though it expired. Congress did pass a continuing resolution bill. That also included a $13 billion transfer from the general budget of the United States to the Highway Trust Fund to make up the difference. They still are going to have a problem, though, of running out of money in 2022 because the extension's for 1 year. But it does look like any additional infrastructure spending this year is unlikely, especially with the election. So after the election's over, there is a possibility of something happening. Congress itself is operating under what they call a continuing resolution. They have not passed a true budget. So for the remainder of fiscal year 2021, which will go till next September, we still don't have a budget to rely on. The transportation construction community, which is all the DOTs, have been advocating or lobbying for the U.S. to provide those DOTs an extra $37 billion in aid because of the fact that people aren't traveling. And so that Highway Trust Fund, which relies on gas taxes, the money's dropped even more. And so the state DOTs are wanting the U.S. to help bail them out a little bit due to the COVID-19 situation. So that brings up an interesting issue with the election. So the FAST Act, which does essentially highways and streets and surface reauthorization work that I just mentioned to you, which was the fill-in for the lack of money in the Highway Trust Fund. This FAST Act could have a new approach done if the government stays as is. Kind of doing the same approach, just in addition to a new FAST Act. If the Democrats end up winning the entire House and presidency, then they actually already passed a new bill called Invest in America Act, which will kind of redo how we fund our highways. And in terms of infrastructure, which would include not just highways and streets, but all things infrastructure, from levees, dams, those kind of things. If it stays as is with a divided government, chances are slim for a broad infrastructure bill just because of the divided government. But again, if the election ends up being a sweep, more than likely we'll probably see a big infrastructure stimulus bill come out. They had actually talked about doing that back in March and April as part of the CARES package. That did not happen because of the COVID spike. But it's interesting to note these possibilities here, but these are what a lot of the lobbyists in Washington are hearing, and then we get reported back to on. So that kind of gives you an idea of our forecasts and our government affairs. If you guys have any questions with regards to any of these topics, feel free to email me, or you can ask questions now. This kind of concludes my presentation, but if you go to our website, there's all kinds of information there. As I mentioned, if y'all want to become members, I can get you a free design guide. You just need to let me know that. To become members, just click on the link here. But we do have access to webinars, technical data, things like highways and streets on CRCP, that kind of thing. With that, I will close, and I appreciate y'all's time. I'll hand it back to you, Momin.
Perfect. Thank you very much, Rob. That was excellent. So before jumping to our last presentation, I want to remind all the attendees that tomorrow we will have part 2 of this webinar that will discuss, again, the corrosion management of transportation infrastructure from 3 further perspectives. So I have added the link to the flyer as well as the registration link in the chat box. So feel free to attend it tomorrow. So now let me share my screen first. So now I will introduce our last presenter, Dr. Steven. So Dr. Steven is a university professor with a career-long history of working in higher education with strong industry links. Dr. Steven's academic qualifications bachelor and PhD in metallurgy from School of Metallurgy, University of New South Wales, Sydney, Australia. He has extensive experience in materials science and materials engineering, welding metallurgy, and welding engineering, failure investigations, and corrosion. Dr. Stephen has been acknowledged with International Authority on the Corrosion Protection of Steel Reinforcement in Concrete and specifically galvanized reinforcement for use in reinforced concrete construction. So now I will start Dr. Stephen's presentation.
Good afternoon, ladies and gentlemen. Stephen Yeomans here in Canberra in Australia, so a long way away, but the marvels of modern technology. Well, today I've got a brief presentation prepared for you, as you can see, just on the galvanizing for corrosion protection of rebar in concrete. And I'll work my way through that very quickly. As a bit of an overview, just to let you know that galvanizing has been around, galvanizing of rebar has been around since the 1930s, but particularly from about the late 1950s, early 1960s, there's been a tremendous use of galvanizing pretty well around the world. And here are just a few examples. Bridges, highway construction, coastal and marine, buildings. That's the Bank of Hawaii building in Waikiki, been there since the 1970s. An aquarium down here in Taiwan being constructed, major beam infrastructure in Bermuda, and these are precast pipes manufactured for a sewage outfall facility in Singapore. So very, very wide use, and a lot of this has been well and truly reviewed in documents along the way. Now, there are many ways in which galvanizing can be undertaken, but the two common processes that are used for reinforcing steel are the traditional hot dip galvanizing, which is a batch process. This involves immersing zinc in a bath of molten zinc. And of course, that process is widely available through pretty well all your local galvanizers well across the country. More recently, the last 2 or 3 years or so, continuous galvanizing has been developed. Now, this has come from the oil and gas and tube and pipe industry, where it's a very common process. This is an inline process where multiple straight bars can be galvanized continuously. Now, this is available now commercially in the USA at a plant in Catoosa in Oklahoma, in China, in Xiamen. There's a pilot facility in the UAE in Dubai, and a new installation is being planned for India. Okay, so traditional batch galvanizing as it is, there's a schematic of how this works. You're probably pretty well familiar with this, but the product moves through a series of baths, cleaning, rinsing, pickling, and pre-fluxing. And then this is the key part here, that the product is immersed in a bath of molten zinc for a period of time. Now, with reinforcing steel, these two photos down the bottom here show typically how straight lengths of bar are galvanized. They need to be put into cages or frames and then taken through the process. So this is very typical of commercial batch galvanizing. And these are the types of products typically produced by galvanizing. Obviously, a large amount of straight product is galvanized, and the length of these bars would depend upon the capacity of the bath. Things like mesh, stirrups and ties, which can all be pre-formed, they can be galvanized. And down the bottom here that's a large prefabricated column form that would be completely prefabricated, welded, and then the whole thing is galvanized. And again, the size of these products is determined by the size of the bath that you have available. With continuous galvanizing, as I mentioned, this has come from developments or long-term use in the oil and gas and pipe and tube industry. Straight lengths of bar are put through a facility where they are blast cleaned, a flux is sprayed on, they're heated, and it goes through a zinc trough, and the steel is only in that zinc trough for literally a few seconds. And then an air knife cuts the zinc, the fresh zinc off the surface that's residual, and the product comes out the other end. It's a very quick, efficient inline process. And literally it takes but a few minutes from beginning to end to take lengths of straight bar, and here they are. That's a photograph from the plant, and here's the bars going through some of the rollers and the finished product. It's a very quick, efficient process. The thing about the CGR coating, as it's called, continuous galvanized reinforcing, it gives you a uniform thickness up to about 70 microns. And one key thing about this is that you can use silicon-containing reactive steels. That is a bit of a problem with traditional galvanizing, because the high silicon level in remelt steels can cause the zinc coating to grow in an uncontrolled manner. So you need to be careful of that. But with continuous galvanizing, because the steel is only in the zinc bath for literally a few seconds, and because of additions that are made to the zinc bath, a small amount of aluminium, the nature of the steel does not have a long-term effect on the coating, or any effect on the coating. And of course, it's essentially a pure zinc coating on the surface. And here are just a few pictures, this one here particularly, showing how tightly you can bend this coating without cracking or damage. There are a variety of standards that describe galvanizing of reinforcing steel. There are many international standards that have been written, particularly for rebar. The two American standards through the ASTM are ASTM A767, which is for hot dip galvanized product, and the more recent standard, 1094, is for the continuously galvanized. Now, these two photographs here are fairly typical of the type of microstructure that develops with the different galvanizing processes. On the left, you've got the traditional batch galvanized, hot dip galvanized. And as you can see, it's made up of a series of alloy layers. Here's the base steel down the bottom. And then you have the zeta layer here. There's a gamma layer, the zeta layer. Key thing is there's a layer of pure zinc on the outside of this coating, which is typically 40, 50 microns or so thick. Now, ASTM 767 for one class of coating specifies a minimum coating thickness of 85 microns. This coating that's produced on typical steels generally is in the range from about 120 up to about 180 microns thick. And that is determined by the thickness of the bar that you're galvanizing. The key thing is ultimately there is still a layer of pure zinc, the eta layer, on the outside of this bright galvanized product that's 40 to 50 microns thick. Now, with continuous galvanizing, 1094 is the relevant standard. That has a requirement for a 50 micron minimum thickness on the coating. And here's a typical micrograph of that. Now, these coatings typically get up to about 70 microns thick, but this is basically a 50 micron, minimum 50 microns thick coating, which is essentially equivalent to what is here on the outside of the bar on a bright coating. The difference is, of course, here that because of the very short time that the bar is in the molten zinc bath and the small alloy additions that are made to the bar of aluminium, these layers that form in the longer period of time for batch galvanizing don't form with continuous galvanizing. So essentially, it's a pure zinc coating on the outside, and that allows it to be quite formable. Now, let's talk a little bit about what happens with zinc in concrete now. The first thing is, what we know is that galvanizing has a resistance to both the effects of carbonation and also high chloride tolerance. Now, carbonation is a natural process that occurs in concrete due to the neutralization of the highly alkaline environment of concrete as acids from the atmosphere, carbon dioxide, and in polluted areas, sulfur dioxide, nitrogen dioxide, they dissolve in water as it rains, and these absorb into the concrete surface. Now, the minimum pH of concrete is typically around about 12.5 to 13. And this diagram here, classic diagram, shows the corrosion rate of zinc over different pH ranges. And you can see that zinc has a very low corrosion rate over this range from about pH 9 up to about pH 12.5. So what we find is that zinc is much more able to resist the effects of carbonation, which reduces the pH of concrete from 12.5 to 13, down to about 11. And at 11, black steel in concrete will start to depassivate and corrode. That doesn't happen with zinc because it has this actually increasing corrosion resistance as the pH is reduced. Now, carbonation is not a common problem, but it is one of those things that can occur in very thin elements like precast elements and in high water cement ratio concretes and also in poorly compacted concretes. In good quality concrete, it should not be a problem. But the fact is that the zinc can resist this effect, so it's one of the advantages that it has over black steel. Now, the other more important issue, though, is the chloride resistance of galvanizing. And what we know from a large amount of laboratory and field studies is that galvanized steel can tolerate chloride levels in cement and mortar and concrete well above that for black steel. What we find from field studies, and I've got an example of some data coming up, is that you can get chloride levels, 4 to 5 times the ACI recommended levels for corrosion of black steel. You can find those very high chloride levels at the depth of reinforcing bar, galvanized bar, but without any significant corrosion occurring. Now, the ACI level for black steel is 0.4% by weight of chloride in cement. With galvanized steel, an assumed threshold is 1% by weight of chlorides in the cement. So a conservative estimate of the chloride resistance of galvanizing is that it is about 2 to 2.5 times above that of black steel. Now, down the bottom of that slide, I've just shown you a collection of data that I've managed to put together and published this recently in a new chapter in a book coming out later this year or early next. And you can see all of that research that's been done from the 60s right through until the mid-2015. And you can see the different rate or the different change in threshold, 5 times, 2.5 times, 3 to 4 times, up to, 3 times. That they are traditional levels that are recorded for the threshold of galvanized to chlorides. Now, the reason we get these variations in this threshold is because of the nature of the zinc coating itself and also the nature of the environment to which they're exposed, the types of chlorides, whether they're embedded chlorides or whether they're chlorides that have ingressed from the atmosphere. But commercially now, and scientifically and technically, it is well assumed that the chloride level is about 2.5 times that of black steel. Now, here's just some other data. This is a bridge survey that was done across a number of US bridges. You can see there bridges built in the 70s, basically, and inspected at various periods of time. Here are the chloride levels. And remember, there is a 0.4% kilograms per cubic meter for black steel. And here's the coating thickness of zinc left on the surface measured. And what this shows is that, in this data alone, which covers about a 40-year period or more, 50-year period when these inspections were done, about 40 years, chloride levels up to 5 or 6 times that of black steel. Now, just recently, a bridge in Bermuda was demolished. It was the Longberg Bridge. It was demolished because it was badly damaged in a hurricane and needed to be replaced. And some steel samples from that were recovered. And after 70 years of exposure, this bridge was just demolished earlier in 2020, there was still 300 microns of zinc left on the surface. Remember, the ASTM requirement is a minimum of 85 microns of zinc. So what this is showing is that in the field data, zinc can tolerate these very high levels of chloride without any significant effect. Question then becomes, what happens when the zinc in concrete does depassivate? It will depassivate, of course, when you get very high chloride levels coming through. And what we found in laboratory studies, but also from a number of field investigations, is that when the zinc starts to dissolve from the free zinc area on the surface of a hot dip galvanized bar, And that's the galvanized layer here that's been affected by chlorides and has depassivated. The corrosion products that form, which are primarily things like zinc oxide, these products actually migrate out into the adjacent cement matrix. There's a sand cement matrix out here. And what we found is that this often is of the order of 200 to 300 microns and even further, that the zinc corrosion products migrate into the concrete mass. Now, these zinc oxide products are friable, they're powdery, they're not loose and voluminous, such as iron corrosion products. They're non-expansive, and since they don't precipitate at the surface of the bar, they don't cause the distress in the surrounding concrete layer. And some very detailed work has been done on this over the years. And what it's found is that these zinc corrosion products, when they migrate out, they fill microcracks and pores and voids in the matrix. They densify what's called the interfacial zone along here. And that effectively reduces the permeability of that zone. So even though the zinc is starting to corrode because it's been depassivated, it does seem, and there's good evidence to suggest, that there is still good long-term protection for two primary reasons. Firstly, you've got a lot of zinc that remains on the surface, and that needs to be removed from the surface before you get to the steel underneath. So there's a delay in the corrosion of the iron because of the zinc layer. And also the improvement in the densification, the reduction in the permeability of the interfacial zone does help to prevent further diffusion of chlorides and the like to the surface. So let's talk a little bit about the design side and fabrication. Experience over many years has shown, and this has been well documented, that galvanized reinforcement is a direct replacement for black steel in all reinforced concrete design and construction. There's no need for increased embedment lengths as you have with epoxy coated bars, for example. There's no specific design considerations. No special concrete materials are used. The mix requirements are the same. The site practices are the same. And overall, this means that you've got significant design and construction simplicity. You can incorporate galvanized reinforcing steel into your design, obviously for the purpose of giving long-term corrosion protection and reduction of requirement for maintenance for many, many years. And it's a direct replacement for black steel. So that's a significant simplicity that applies. Just to show you this sort of data, new high-strength galvanized bar getting up to 500 MPa. Questions often asked, what's the effect of galvanizing on the properties of the bar? Well, in fact, there is no specific effect. The temperatures of the zinc bar are only around about the 450 degrees centigrade mark. This is well below any temperature to cause significant change, any significant change in the properties of steel. And it certainly doesn't change the properties of high-strength bars. So here's some data from 500 MPa bar, which is becoming much the norm these days. Tensile strength, bending, and toughness, all very, very similar to the ungalvanized conditions. So you've got no particular issue with the change in characteristics of the steel. The other important issue is what is the bond capacity of galvanized bar in concrete? And what we know is that there is very, very strong adhesion between zinc and the cement. And that's because of the similarity between zinc and calcium. Of course, they're very close together in the periodic table. And when zinc is embedded in concrete, there is a very tight adhesion of the cement paste. What we find is that the bond strength of galvanized bar then is certainly no less than that of black steel and is often significantly higher. There's a little bit of a cautionary note here though, is that if you measure the pull-out strength of a galvanized bar in concrete at 7 days or 14 days, you may find that it is below that of black steel, equivalent black steel at the same time. This is because zinc oxide, which does come off the surface when the concrete is freshly exposed onto the zinc, is an inhibitor. It does slow down the hardening of the concrete. But by about 14 to 28 days, when the concrete is well and truly hardened, that process has completely stopped, and then the bond of galvanized bars is generally significantly higher than that of equivalent black steel. So there's no question about change in the bond. And the slip of galvanized bar is also less than that of both black bar and fusion bonded. And here's some data. My colleague and I prepared this data some years ago, back in about the early 2000s. We used ASTM A994 beam end samples to test this. And here's the load slip data for ribbed bar. And you can see the fusion bonded shows the greatest slip. There's the black bar as the norm, as the comparison. And here's the slip for galvanized bar. And the reason for this, again, is because there is very significant adhesion of the cement to the galvanized surface. There is virtually no adhesion with fusion bonded epoxy bar, and there is very limited chemical adhesion of cement to black steel bar. But galvanizing is very much better than that. So the bond strength is as good as, if not significantly better than black steel. The slip is significantly less. Now, in bridge and highway application, here's just a few slides showing some classic examples of the use of, this is hot dip galvanized product, of course, in bridge approaches, highways, here and here. And in this bridge structure, there's the bridge deck, and there's the New Jersey crash barriers in between. A tremendous use, thousands and thousands of bridges across the country, and other types of structures have been galvanized in this way. And also bridge footings and columns in preparation for other infrastructure and buildings and the like. Again, using galvanized reinforcing steel is very common, particularly with high salt conditions in coastal environments and humidity coming from prevailing onshore winds and the like. The high chloride tolerance is key to this protection. Now, let me just sort of wrap up now. Here are a couple of recent examples that I've come up with. This very significant construction is the Mario Cuomo Bridge in the Tappan Zee area of the Hudson River north of New York City. The old bridge was completely demolished and this new one was put in place, and it was only opened, I think, about the middle of last year, middle of 2019 it was open. For all of this structure, it's 3.1 miles long, has approach spans that run off onto the foreshores on both areas, a lot of columns, and these main central supporting areas with the cable stayed bridging in the middle. All those pairs of support towers, the twin towers, the approach spans and abutments, there's some 40,000 tonnes of galvanized, hot dip galvanized rebar in that. And the New York State Thruway Authority has designed this for a minimum 100-year life. And also, well, there's the columns of the central support towers being fully reinforced with galvanized bar. And here are some of the 6,000 hot dip galvanized reinforced precast panels that form the road deck for that 3.1 mile span. So that's a major new infrastructure. Just here's some interesting information gleaned just recently. And this is just a few examples of state departments of transport and the like who are now routinely specifying galvanized rebar. Rhode Island DOT is using it for their largest design build project, the Route 610 interchange. Connecticut is using it in all future bridge designs. The New York State Thruway has been using it since the 95s. And there's the comment that they made about the Cuomo Bridge, designed for no major maintenance for 100 years at least. And of course, Bermuda is the classic example, and they've got some 60 to 70 years use of hot dip galvanizing in all types of construction. Now, on the continuous side, this has not been around for quite so long, but this was the first bridge built in 2018, I recall. This was a local community bridge in Iowa, the Buffalo Creek Bridge. There's the installation going in, and here's the fitting of the decking bars and the feet for the edge. About 75 tonnes of CGR used in that. of that new regional bridge. And since that time, there's been a lot of other applications of the continuously galvanized straight bars in apartment building, balconies, sea walls, some precast construction, general construction across many, many areas of the US and in Bermuda. And this is a recent example, a very good example of the use of CGR. This is Vermont Transport have built this new rail tunnel in Middlebury in Vermont, 422 continuously galvanized precast wall and roof segments, and there's the layout of the reinforcing steel and the precasting panels. And this long tunnel replaces two very old bridges right in the center of this township and encloses an existing rail cutting. And here's the form of it. No roof on this here, but here are the precast panels that have been put in place and linked together. And here's the construction, ongoing construction, fully closed over with the roof. So here's a very good example of the use of this type of product. Okay, well, that's about a quick run through. There's obviously a vast amount of information out there. If you want further information on this, there's the Galvanized Rebar site that's available through ILSRO and the Galvanized Association. Here's a document that's been published by the International Zinc Association, which also contains a lot of information on reinforcing steel. And I've got to give myself a bit of a punt here. That's the book that I published with contributions from some international authors around the world. And it contains a vast amount of information on the applications and use. And since that time, of course, there have been some other significant publications that have come out, and also a couple of chapters that I've written in books that are coming out very soon. Okay, well, that's a very quick run through. Thank you for your attention. If you've got any questions, the team there will attempt to answer them for you. So all the best for your seminar, and cheers from me. Goodbye now.
So thanks, Dr. Stephen, for your comprehensive presentation. So this concludes the presentation portion of our webinar. Now we will start receiving the questions from the attendees. So I can see the first question in our chat box. It's to Homero. So the question is, in all the experiments, the pH of the electrolyte and the temperature were kept constant, which is not the actual case in practice. Would the results have been different if there were variations in the pH and temperature?
All right, so can you allow me to share my screen moment? Because I want to answer that question by sharing something.
Okay, so you should be able to share your screen.
Really? Okay.
But yeah, I need to stop sharing my screen.
You need to stop sharing. Yeah. All right. Thank you.
Okay.
Well, who did the question? Olani. All right. Good question. The answer is yes. It will be different results, and this is a schematic of things of how many parameters we have that will affect, of course, the corrosion rate, because all are precursors of corrosion. Now we are doing a model in terms of level of, let's say, critical level or ranking of parameters. The ranking of parameters comes from the precipitation, humidity, relative chloride content, and one of them is temperature. So of course the temperature and also pH, as you see, based on the CO2 content, and we change the pH, we will have a different effect, of course. So the first approach that we do is right now with pH fixed control. No, fixed control, it means that we are in a certain scale, but fixed is different. We need to use a buffer. But in terms of pH, yes, it will give us different results. However, I do believe that the results will be meaningful if we go and explore the variations. That's why I want to show these transparencies and also answer the question. Variations means what are the limits in terms of the field? In the field, as you are right, the macro external parameters, for example, the total chlorides are certain, and I will show you the ones that I think one of the questions, the temperature. The temperature, we have certain ranges that we are going to explore I mean, we cannot explore everything in the lab, but we can explore 3 or 4, and we need to set the conditions that we face, the limits, and also the pH based on the CO2. The CO2 acidifies the concrete and therefore will change the pH to see the changes in the variations of the results. But the answer is yes. All right. And that's why I just elaborate more of the answer.
Okay, thank you very much, Dr. Romero. So the second question, I have a question from my side. So actually, this is not my area of expertise, since my expertise is more into asphalt and pavements. But I would like to ask Rob about the impact of using these galvanized rebars in continuous reinforced pavements. So you mentioned in your presentation that it has been used in the concrete pavement. So I'm aware that many of the failures that occur in concrete pavement results from the corrosion in the rebars. So have this been done before, or is there any like an approximate extension in the service life in the concrete pavement due to using these galvanized rebars?
I think it's on the bridge. I don't know if someone wants to elaborate. I will ask.
I would like to hear Dr. Romero and Rob's both of your point of view on this question.
All right. Yeah, I'm going to answer first. Is that okay, Rob? And then you go.
Yeah.
All right. So then from my perspective is that it's not only the pavement. I just show the on the bridge, and it's on the deck side. And maybe there is some elements in the, there are elements that are already right now, they use galvanized rebar. And basically is that theoretically means the schematic that I show is gonna last more the initiation time. The initiation time for sure is gonna be more than the black steel. But the thing is, the mechanism that we need to explore is when we don't have any more zinc protecting the rebar. Now you have a bridge between the concrete and the rebar. But since the zinc still is sacrificial, and we have active zones, then it will, my guess and my hypothesis that will extend also the other stage, all right, the propagation stage. And also this is not only the corrosion side, and we are also studying the corrosion product side, which is more the loading, the stresses that are induced due to the fact that you have corrosion products. The corrosion products are, as I mentioned, and I think it's well documented that is less volumetric. The corrosion products of the zinc, the hydroxides, the oxides are less volume, and also more uniform. So from my point of view, of course, that the schematic shows that you extend the life based on the galvanized use, all right? And of course that it's right now, prediction-wise, all the models that I already built, we already built it looks like and shows that yes, the galvanized layer will extend the life, all right? That's my approach. Rob, please.
I don't have a lot of experience with galvanized rebar. But I do have some experience with galvanized decking in parking garage applications or on concrete. There were some issues, and that's a G60, G90 spec, where you're getting a certain amount of fluid ounce weight on each side of the decking. There were some problems with the galvanizing, and I'm not sure, I don't know the chemistry behind it, but there were some problems with the galvanizing deteriorating faster than anticipated in those situations. And I don't know if that was because the patina was not allowed to form in the galvanizing prior to placing the concrete on top. But and essentially, if you had a parking garage with galvanized decking, sometimes the water that would permeate through the concrete, either through the porosity or the cracks, it would stay there and then not get out. There was no way for it to drain off. And that was the process people thought of doing that. Now, that being said, I know on structural steel, the galvanizing that was in use on seashores where high chloride concentrations were kept, they did see a little bit more rapid deterioration of the galvanizing. So again, not knowing the chemistry of it, that was some of the resistance to when I was pushing structural steel that was galvanized to salt-laden environments. That being said, in an environment where galvanizing was exposed to the atmosphere, they were getting very long service lives. So that's the extent of my knowledge.
Okay, thank you very much for your comprehensive answer. So the next question is to Dr. Homero. Is the service life prediction based upon the area corroded or the loss of rebar thickness?
Okay. All right. This is from, oh, Ivan. Hi, Ivan. Yes, let me answer you in this way. I have transparencies for everything. So we have two approaches. I think that we explained two approaches. And to answer your question first is that it's the classic way to predict the probability of failure, and also for the reliability classic. What we are doing is the thickness, the loss of thickness. That's how we use the probability model. But also what we are introducing is the probability of failure based on the pitting. So it's gonna be, we're gonna build the model. First, the corrosion model will be the probability of pitting based on pitting density and based on the depth of the pit, all right? So that will be the other model that we are building. But again, the answer to the question is the thickness. I think that you, that was the question is, and that's why I showed the thickness, because it's the loss of the capacity based on the loss of rebar thickness.
Okay, great. So the next question, so again, this is to Homero and Rob. So again, I would love to hear your point of view on this question. So the question is, can we extrapolate the results in any little sense to a coastal location to tell the final users that with galvanized rebar, we can guarantee several years of service, between brackets, more than 80 years, or how much time in such coastal location we can expect of a structure which was built using galvanized rebar? I witnessed a very big parking garage at Veracruz Harbor, Mexico, which could reach 80 years of service according to the galvanizer. Is that accurate?
Yeah, I can have my, now I'll do my perspective, Rob, but you're first if you want.
Oh, well, again, you know, if galvanizing, again, in my experience, if galvanizing is allowed to build its patina to develop that oxide layer, then yes, I think you can easily get 80 years out of it. That's been the question though. Can it do that? And if there's a wetting drying cycle that's allowed to occur, I think it can.
Yeah, especially in this, I've been in Veracruz, by the way, very nice town to do your vacations also, not only petroleum town, but Veracruz is very aggressive. They do have a very high HR and also temperature. So the swings of corrosions are very challenging. So based on that, Veracruz has a very good environment to corrode. And in terms of the structures or the RC systems, you have we have now the concept of, and also that's in pipelines. Everywhere is time of wetness. Time of wetness is how much the water is touching the surface of the substrate or the rebar. In that case, then you build your model based on the type of wetness that is especially in these areas that has high humidity and high temperature and high salinity. So you reach already the threshold. So let's assume that you have in coastal zones, you already have 3.5% or so. That is way beyond the threshold. So it's just when it touches the rebar, it's gonna react. And I agree that the key ingredient is the corrosion product. How it's gonna be formed, how it's gonna be distributed, all right, on the surface will make the difference to last longer. 80 days is feasible. So to answer the question,
I'll add, there's a similar product, ASTM, I think it's 538 or something like that, Core 10 steel. It works on the same premise where it can develop the patina layer that stays bonded to the original surface very well. They call it weathering steel on the structural side. It performs very well, but not if it's not allowed to wet and dry. It's the same kind of thing. And so I think that's the key, is in the environment you're putting this in, is it going to be allowed to do that? And I would actually, and Homero, you correct me here, because I am not a chemistry guy, but I think if you could allow the galvanizing to, quote, cure and allow it to develop that outside of the concrete before you place it in the concrete, I think that problem might be alleviated. Would that make sense?
That makes sense. Yes. Just reaching the phases that are more prone to sacrifice and do a very nice, again, the surface is everything for everything, guys, in terms of corrosion. So I think that, yes,
Exactly.
to cure or to, let's say, transform the phase that you want to have. And I think there are some processes now that they allow to do that. So, I mean, galvanized industry is moving, even though it looks like a very simple process, but are moving in a way that they optimize the process. So yes, again, the secret is the corrosion product formation. So,
and I will say what people don't recognize, I did not know, is that the amount of galvanizing you get in the manufacturing, in the whether it's the hot dip process or this continuous galvanizing process, you're actually getting more product than you typically specify as a minimum. So you're, in essence, getting more protection. And I don't know if people take that into account or not. You design based on what the spec calls out for, but usually this process, depending on the thickness of the material, is going to give you more galvanizing than you're actually designing for. So you're going to get a longer life than you think you're going to get from a pure design standpoint.
I see. Oh, Emmanuel. Oh, I didn't see who was the one that was asking. But yes, I think that the target that I am hearing, I don't know if you hear also, Rob, but the target is 100 years, more than 100 years. Is that right? So now the target is 100 years, so 20 more years of that 80. So that's why we are making, I mean, different materials, not only in the galvanized, but also you heard the rebar is also putting a different material, different composition to reach that goal, the 100 years goal.
And I actually recommend that, engineers and owners specify galvanized rebar or some sort of coated rebar in any exterior application, just because in practice, the concrete can become very porous if not properly consolidated, mixed, and cured. And it just gives you a little extra protection for not much cost. Galvanizing will definitely extend the life of a structure.
Yeah, all right.
Okay, so I can see another question. It's why doesn't CRSI have ASTM specs for CGR?
There is one. It's the 1094, 1034, but we don't. I think I answered that one. We don't specify. I mean, that's up to the manufacturer. We just reference it, but it's up to the person making it to get the ASTM standard. They have to supply the testing, the procedure, and the verification behind it.
Okay, great. So I can see a comment from Dr. Stephen, the third presenter. So I'm not sure if he is here. Can he answer this question or add the comments that he added in the Q&A box? Let me try to allow him to.
Oh, that's Dr. Stephen is there.
Yeah, Dr. Stephen, now you can answer the question or add your comments that you added in the Q&A box if you would like to do so. Otherwise, I will read your comment.
You are on mute, Dr. Stephen. You're on mute. All right.
Hello, can you hear me?
Yeah, we can hear you.
Yes.
Oh, hello there. This has been great. I've been listening into all of this very early in the morning here for me, but the sun has now come up. Yeah, look, this has been terrific. A very good set of presentations. I'm very pleased to be part of it. Look, just a couple of comments that have been made about the service life of galvanized bar. What we know from field studies, and we've now got bridges and other structures that have been examined getting up towards 50, 60, 70 years in age, is that it can tolerate the very high chloride levels. And once even if the galvanized bar does depassivate, if you've got excessively high chloride levels and you've got poor quality concrete, even though the zinc starts to corrode, the corrosion products, of course, tend to blanket the surface. They're not disruptive, as are black steel products. So therefore, the damage is minimized. There is no real cracking of the layer of the cover concrete. And you've still got that reserve of zinc on the surface. And so it takes a lot longer for the black steel to be exposed. With ordinary reinforcing bar black steel, if it's in concrete, the life is often taken to be this time for initiation of corrosion, because once the black steel depassivates, the corrosion process continues quickly, and the damage, the cracking and the staining of the concrete will occur very, very soon thereafter. But there's a significant delay period in that with galvanized bar because the zinc corrosion products do form, but they get trapped in the matrix, and you've got that reserve of zinc that's left on the surface. So there's been some predictions about service life. Compared to the initiation time for black steel, the service life for galvanized steel is sometimes reported as in the order of 4 to 5 times longer than the initiation stage for black steel. And that's due to the combination of the delay in initiation and then the protection that is still afforded when the zinc might start to corrode. The other thing, of course, is that zinc in concrete is a very different environment to zinc in the natural atmosphere. In concrete, there is an immediate reaction between cement and zinc when the cement is still wet, when the concrete is still wet. That reaction lasts for 4 to 6 hours whilst the concrete initially hardens. Once that hardening is finished, then the zinc is in a very stable situation. And a couple of comments that were recently made about forming the patina on the surface, that passive film will form on the surface of zinc in that first few hours when the wet cement is in contact with the zinc. So there's a lot of chemistry about that. There's been a lot of research done by Carmen Andrade and others in Europe. And that was a lot of the work that was included in the book that we published back in 2004. So it's all very current. But there's a lot of understanding of the reaction of cement with zinc. And certainly once the zinc is passivated within the concrete mass, it is very stable for a long period of time. And the thickness of the zinc layer, the extra microns, 40 to 50 microns on top of the batch galvanized bar, and the 60 to 70 microns on a continuous bar, that's what provides the very long-term performance. So therefore, life is extended over the initiation of black steel, and we see there is a distinct reduction in the need for maintenance, and the intervals between maintenance are very much longer with galvanized bars. A comment was made about Core 10 steel. Of course, Core 10 steel does require that very specific atmospheric condition for it to provide its patina on the surface. And that's for natural exposure, but it does not work within concrete. Core 10 steel behaves in exactly the same way as ordinary black steel in concrete. And the reason is that the patina that protects Core 10 steel in the natural atmosphere cannot form within concrete. So just a couple of comments there for you. I hope that's assisting.
Yeah, that assists a lot. Thank you very much, Dr. Stephen. So I think this summarizes our webinar. Before that, I would love to thank Alan. He provided a successful example of reinforced concrete with galvanizers. It's Auto Route 40 in Montreal, Canada. So I do want to thank again all the 3 presenters. I think this really turned out to be a very well technical program and presentation. Again, I want to thank the attendees. Please let me know if you have any questions about the webinar series and about Tran-SET. Otherwise, have a great rest of your day. Thank you.
Thank you all.
Thank you.
Cheers.